Hey, good morning, guys. We're going to look at 7.5 notes here on parametric equations. So it's still going to give us a graph that looks just like a normal quadratic equation, or no, sorry, normal equation on the coordinate plane. But the way we go about it and the meaning is going to be a little bit different. So our objective is to graph parametric equations. The first thing I want to look at is the difference between a rectangular coordinate graph and a parametric graph. So we're still going to have a coordinate plane with an x and y axis. That's not going to change. In the first example here, I've got just a rectangular graph of a parabola, and you can see our function y equals x squared minus 2x minus 3, and the graph of that function below. And so what a regular coordinate, rectangular coordinate graph does is it just compares the x values to the y values and shows those corresponding parts on the graph. A parametric equation, we go about it a little bit different, and it actually breaks a function up into two different equations. And so it's telling us how an x-coordinate is behaving at a given time represented in t normally, and how the y-coordinate is behaving at a given time. And so we're looking at two different parts. And so we've got a lot of things happening in a graph that's a parametric graph. So in this case, we have two parametric equations, but they are still going to represent a parabola, and the graph of that is below. So what we do is we actually have a t-chart, but it's got three columns in it. And so in this particular example, they put the t all the way on the far right. I usually start out my columns with a t, and so those are our input values into each the x equation and the y equation. So what happens is I would substitute -3 in for x. So since x is t plus 1, I would say, well, that's -3 plus 1, and so x is going to equal -2 there, which you can see my -2. And then for my y equation, I'm going to substitute -3 in for that one. Negative of -3 squared plus 4. So that's going to give me -9 plus 4, which is -5. And so there's my -5. The result then is the ordered pair -2, -5. And I would still plot my points just like that. And so my -2, -5, you can see is right down here. But then we add to that what the t value is for that point. So when t is -3, when the time is -3, then we have a point at -2, -5. And so we want to list that. And we would go around in our t-chart for all of those values. So you can also see that we have in our next point, when t is -2, we have a point at -1, 0. When t is -2, we have a point at 0, 3. When t is 0, we have a point at 1, 4. When t is 1, we have a point at 2, 3. At t equals 2, we have a point at 3, 0. And then t equals 3 at points, let's see, 4, -5. And so you can see we get that parabolic shape. The other thing you see here, these are actually arrows, okay? And it's showing us the direction that as time increases, what's happening. So when we first started it at t equals -3, and then you can see the direction of the graph. Those little arrows are telling me that the next value is when t was at -2, and so forth. So that's what's called the orientation of the graph. These arrows are the orientation. Just telling me what direction it's going. Typically, when we look at a parametric equation, or a lot of times, not always, in this case, it's letting us really have a limitless value for t, but a lot of times what you'll see is it'll give restrictions on t, which is your parameter. And so if I were to put dots at -3 and at 3, and I would just terminate the graph there, then on the parameter t, I'm putting the restriction of t is greater than or equal to -3 and less than or equal to 3. And so that just means that we're not going to have any values outside that domain. All right, so let's look at the next page. So let's just look at a parametric equation. It says parametric equations are a set of equations that express a set of quantities as explicit functions of a number of independent variables. And our independent variable is t, which is the parameter. So it's saying that x is going to behave this way given t, and y is going to behave this way. And again, a lot of times, if there's no restrictions on t, we can just have a normal parabola or whatever function we have with arrows, if that's the case. If we use restrictions on t, so let's say t is less than or equal to some number t is greater than or equal to some number and less than or equal to some number, then we would restrict our graph and it would have endpoints then. Rectangular coordinate form. So a normal equation, obviously we just have x and y coordinates. We don't have a third t coordinate. It says in parametric equations using variables, what do we do there? So to write a parametric equation in rectangular form, so let's say we're given x equals something in terms of t and y equals something in terms of t, and we want to change that to a normal rectangular equation. That just means on a normal coordinate plane with just your y and your x in one equation. So the list of things that we would do is we would solve each equation for t. Then since both equations are equal to t, they're equal to each other, so we set them equal. And then we're going to solve the resulting equation for the rectangular form that applies. So you have to kind of pay attention because it could be a line, it could be a parabola, it could be an ellipse, hyperbola, any form really of equation. So you've got to pay attention to what you have. And we'll come back to that list here in just a second. Before we move on, we're just going to look at how to graph a parametric equation. So I have x equals 2t minus 5. I have y equals t squared plus 4. And I can see that I have a restriction on my parameter, that t is restricted to -2 to 2. So I'm going to make kind of an expanded t chart here. I'm going to put my t first, and then I'll have my x coordinate and my y. Now it does say I'm going to be limited to -2 to 2, so I'm going to start -2, maybe -1, 0, 1, 2, try to keep it simple. And then I'm going to figure out what my corresponding x and y values would be. So if t is -2, I'm going to substitute that into the x equation, which would give me -4 minus 5, or -9. And in the y equation, -2 squared is 4, plus 4 is 8. So I actually have an ordered pair -9, 8, where t is equal to -2. Then I do -1. So I've got -2 minus 5 would be -7, and -1 squared plus 4 is 5. So my coordinate is -7, 5 when t is -1. When t is 0, I would have -5 and 4. When t is 1, I would have -3 and 5. And when t is 2, I'm going to have -1 and 8. Okay, so now I'm going to plot that on my coordinate plane. I'm not worried about the t. As I plot each point, then I can kind of identify my t value as well, but I'm going to graph that ordered pair, the ordered pair. So I have -9, 8 that I'm starting with. And that's where t is equal to -2. So I want to indicate that at the point. Then I have -7.5, and that's where t is equal to 1, or -1. I have -5.4. That's where t is equal to 0. -3.5 and -1.8. And so for that I have t equals 1 and t equals 2 respectively. Now I'm ready to graph. And so I'm going to stop there at the 2 and the -2 because I have a restriction. I'm only looking at the parabola where t is going from -2 to 2. And that's my graph. Okay. Okay, so now let's look at it in rectangular form. And so I've got the same problem, but I'm going to change this to a rectangular equation. So in my steps before example 1, I talk through how to rewrite a parametric to a rectangular form. And so the first step is to solve for t in each equation. So I have x equals 2t minus 5, and I have y equals t squared plus 4. So when I solve for t, I'm going to add 5x plus 5 equals 2t, and so t is x plus 5 over 2. Then in my y equation, I'm going to subtract 4, so I have 4 minus y equals t squared, and we're going to take the square root, and I get t is equal to plus or minus the square root of y minus 4. Well, in my second step, since now both equations are written equal to t, if they're both equal to t, they're equal to each other. So the equations, set equations equal to each other. Which means that I have x plus 5 squared would be equal to plus or minus the square root of 4 minus y minus 4. And then since I have a square root, I'm going to square both sides. And so I don't even have to multiply this out because I'm thinking ahead a little bit and I'm seeing that it's going to be a parabola. So I have x plus 5 squared over 4. And on the right side, then that would give me y minus 4. And then I'm going to multiply both sides by 4 because I have 4 in the denominator there. Okay, so my final equation is going to be x plus 5 squared equals y minus 4. Okay, and that's the equation of my parabola. And then we can follow the steps that we did in lesson 1 for parabola. So this one has an axis of symmetry at of x equals -5. It has a vertex of -5, 4. And then we're going to want an additional point. Before we select that, I'm going to plot what I have. So I have a vertex of -5, 4. You'll see in the graph above that it also has a vertex of -5, 4, because this is the same graph. It's just a different way of thinking about this. And my axis of symmetry, of course, is right through here. Okay. And we need to get another point. I'm going to let x be -3. And so for my equation, I'm going to have -3 plus 5 squared is equal to y minus 4, and we'll see what that corresponding y is going to be. So this would be 2 squared equals y minus 4, so 4, and then if we add 4, we get y equals 8. So I have an additional coordinate. I have a point P, I'll call it point P, at -3, 8. Okay, so I can plot that at -3, 8. And then I would have one on the other side. Just going to look at my other graph real quick here. I think it should be -3, 5. Let's see. Oh, I forgot my 4. You feel like you're in class, don't you? Bradfield forgot something. Which is, of course, going to make a big difference for us. All right, so that's 4, then equals 4y minus 16. If we add 16, that's going to be 20, and we get 4y. And so y equals 5. So let's try this one again. So I'm going to have -3, 5 for my point. So -3, 5. And then, you know, we'd have a more accurate graph if we had an extra point, but it should look something like this. And you can see that those same points were on our previous graph because it's the same graph. It's just done as a rectangular graph as opposed to a parametric graph. Okay, so we can have some different representations. Another thing that we can have happen is we can have some trigonometric functions in there. So in the case the parametric equations contain trigonometric functions as parameters, we can write them in rectangular form by using trigonometric identities. So it says write the pair of parametric equations given below in rectangular form and graph the equation. So this time we don't have a t, and I don't want to solve for theta. That's not really going to work for me. So when we have a cosine and sine, I'm thinking, okay, what kind of trigonometric functions do I have with sine and cosine? And of course, we have a Pythagorean identity, which is sine squared theta plus cosine squared theta equals 1. And so that's what I'm going to use. And that is also, if you think about it, that's actually the equation of a circle because it has a radius 1 there. um, or a form of an ellipse maybe. So what I'm going to do is I'm going to solve for sine theta and cosine theta. And then so I'm not going to solve for theta, but I want sine theta, because that's what I'm going to replace in the equation. So I'm going to divide by 7, and I get sine theta is equal to x over 7. And then for the y equation, I'm going to solve for cosine theta. So dividing by 2, I get cosine theta is equal to y over 2. Now I can plug those values into my Pythagorean identity. And so instead of sine theta, I'm going to put x over 7 squared. Instead of cosine theta, I'm going to have y over 2 squared equals 1. Okay, and then square x over 7, so I have x squared over 49 plus y squared over 4 equals 1. So you should tell that this is actually an ellipse, because we see that it's addition in the middle and our denominators are different. If they had come out to be the same, then that would be a representation of a circle. So this graph is going to have center of 0, 0. Because it's an ellipse, we know that the largest number is always a squared. So a squared, in this case, is 49. And it's under the x value, which means that a, which is plus or minus 7, is going to go left and right of the center, because it will be, the major axis will be parallel with the x-axis there. And then b squared is 4, which b then is plus or minus 2. And so that value is going to go up and down for the center, from the center for our minor axis. All right, so center is 0, 0. We said it's going to go left and right 7 units. So those are my vertices, and from one vertex to the other, that's my axis, or major axis. And then I'm going to go up 2 and down 2 along my minor axis for the covertices. And again, because this is an ellipse, we don't have any asymptotes or anything like that. We're just ready to go, and we're going to graph. And we'll do the best we can, but it may not look perfect. That wasn't too bad. Okay, so for these, I definitely would focus on your Pythagorean identities, especially as it relates to conic sections. So you're probably going to want to get out that identity sheet and check out your identities as you're working through some of these problems. All right, I hope this helps. I'm sorry for the delay on the video. I love technology, as you all know. And so hopefully this is better. If you have any questions, please don't hesitate to ask me. You'll want to go to the assignment page for the notes key, and the practice problems. Okay, have a great day, and we will meet again on Wednesday.